Right, let me have your attention and let's start for today. And we will learn more about the virtual memory translation today. And before starting, let me announce that I postponed the due date for the lab 1 to the next coming Monday. So the reason was like that there are some of the students who joined the class in the last minute, so they do need the time for finishing the labs. So like I will remove the 75% due date for it, but accept all the assignment until next Monday, coming Monday. Yeah. And then when you submit the lab 1, so all the submission will go through the GitLab that we are using. So what you need to do is like after finishing the lab, you need to add a tag on your branch and commit and push that to the repository. And so like you can easily do that by following the command line that is specified in the lab document. But if you mistakenly tag the wrong branch or something, then you can delete the commit from the local and remote, and then you can push it again. So deleting the tag does not delete your code at all. So don't worry about that. So if you marked your branch incorrectly, then you can delete the tag and then tag it again and push to the remote repository. And the best way that you can check if your commit is correctly placed or not is go to the GitLab website and then try to check if you can see the lab 1 final tag from the drop-down menu. So that will be the quickest path to check if your tag is committed successfully or not. Any questions for the lab submission and then due date for the lab 1? But for those who finish the lab 1, please start the lab 2 as soon as possible. And then we will learn about the page directory and page table. But conceptually, you can think it as like we will have this kind of a 2-level page directory and table. So starting from the physical address that points to the page directory, that will be stored into the CR3 register. And we will look for the page directory first. So the page directory has like 1024 entries. So the reason is like that we only have like 4 kilobyte pages. And then each of the pointer that we will use is in 32 bits. So that's 4 bytes. So we have 1 kilo entries. So that's why we have 1024 entries are available in the page directory. And this page directory will store the address, actually the physical page number for the page table. And then each page table will indeed store the physical address that the virtual address will be translated to. So please keep this in mind, this kind of figure. We have like a 2-level page directory and page tables. And let's do the recap about like how we translate a virtual address to a physical address. So conceptually, you can think it as like we have a virtual to physical mapping like this. But internally, the Intel CPU do not store virtual to physical mapping in this kind of the table. How we do is like we are using this kind of page directory and page table. We will later see like, why this kind of the structure will be much more efficient in storing page tables. And how we use that is, so we ignore the last 12 bits, the offset part of the page from the translation, because what we will translate is the top 20-bit address. So we will translate the virtual page address to a physical page address. So we are not interested in like translating the addresses within the page offset. And then by cutting the bits of the addresses into 20 bits and then 12 bits, and then we will ignore this part for the translation. And then we will cut the page number in half. So for 10 bits for the indexing page directory and 10 bits for indexing page table. So that means that we can cut off the last 3 digits of zeros here. And then if we split 8048, that hexadecimal number into exactly 10 bits. So because we need to cut the 0 in the middle. So if we cut it into 10 bits and 10 bits, so that's why the lower 10 bits are the same as like the 0x48, but the 8 is like the 2-bit shifted. So that's why we are seeing the index as a 0x20. Yeah. And then after we have each of the index, how we access it is like we will first consult to the page directory first. So 0x20 here means that this is 32nd object entry in the page directory, because hexadecimal number 0x20 is a decimal number 32. And then what that means is that we are referring to the page directory and then referring to the 0x20, 32nd entry from here to find one of the corresponding page table. So by having one access, we can identify where the corresponding page table is in this address. Then we will figure out the corresponding page table. And then we'll use the page table index to index the entry at the 0x48. Then we can get the physical page number 10000. So although conceptually we can think it as like there will be a mapping from the virtual address to physical address, the CPU will internally store the data into this kind of 2-level structure. And then we will use top 10 bits to index page directory and then lower 10 bits to index page table. Then this is how we can translate a virtual address to physical address. Any questions at this point? And then today we will go over a little more about, there was one question from the Zoom side. So the question is that are the page table address in page directory entry physical address of the page table entry or page table or virtual? So all the address that we will store in the page directory and page table are all physical, because we are, so these structures are used when we are translating the virtual address to physical address. That means like if we have any kind of virtual address here, then we are falling into the same problem again. We need to translate that address too. So CR3 and then page directory and page table, they are all storing the physical address. And there is another question on the from the audience.
CR3 is just like an array.
So CR3 is not an array, it's just a one register, 32-bit register. So it only stores the address to the page directory. So the CR3 only stores the address to the page directory. And then whenever the address, virtual address gets applied, then we can know that the directory index and table index. And then by using that, we will go to the page directory first, using top 10 bits, select one of the page directory, and then that will refer to one of the page table. And then using the middle 10 bits to index page table, then we can get the address, the physical address of the virtual address. So that's how it works. So although I depicted this as like one directory and one table, then you can imagine that there will be only one page directory, but that there could be 1024 page tables are available, but we will choose one by using this index. And then today we will learn more about how we can set the page permissions using the lower 12 bits in the page directory entry and page table entry. And we will also learn about like how we can arrange a virtual memory for a good use. And also we will learn how JOS manages physical memory. So let's start with the page directory and page table entries. So I've shown you that there is a page directory and page table, and then each of the page directory entry and page table entry will store, definitely it will store the physical address to the page table or actual physical page. But the interesting thing is that we will only use top 20 bits to store the physical page number or page table address. And then because we are not translating lower 12 bits, we can use these as like some of the additional storage that we can store some of the flags. And then we are actually using these flags in many different meanings. But the most important thing here is that the present, writable, and user. So you can regard each block here as just storing 1 bit. And then if the P bit is the like lowermost bit in the page directory and table entry, and if that value is 1, then means this entry is valid. If that value is 0, then no matter what kind of values stored on here, then that means like we need to ignore that. So the entry is invalid. And then this writable bit right next to the present bit, this one, that will indicate that the memory region is writable. If that is 0, then CPU should block all the write access attempt because the memory area is read-only. And then the last bit is from the last part was like this, the last one, the U bit. So that indicates this memory location is for ring level 3 or ring level 0. So if the U bit is 1, then it's allowed for the user application access. So the ring level 3 can freely access the memory. But if this bit is 0, so PTU bit is 0, then like only the operating system kernel, the ring 0 level, can access the memory page. So we will store this kind of the permission information in the lower bits, and then this slide summarizes what kind of the bits we are interested in for manipulating when we need to set the memory permissions. So there is a PTP. So I just use the same notation that we will use inside the JOS code. So PTP means that like if you set that bit, then the entry is valid. And then if that value is 0, then entry is invalid. And then PTW means writable. So if that value is 0, that's read-only. If that is 1, then the memory area is writable. And then PTU is for user and kernel. So if that bit value is 0, then only ring 0, the kernel can access. But if that value is 1, then it is accessible to user. So by using this, we can control whether the certain virtual memory region is valid or not. And also we can make the memory readable or writable. And also we can enable memory access to only to the operating system or to the application level. And these kind of bits, so I just put it like this. So in the page table entry of the 8048 something, yeah, then like they will refer to this one. Then we will have a physical page number like this, but the page number will be shifted as shifted 12 bits because we will not use the lower 12 bits. But in the lower 12 bits, we can store these kind of flags. And then like I put some of the example flags like this. And then if you read this one, so it has a physical page number 10000, and then it has a flag like a PTU and PTW. What that means is that like it's readable for the user, but the writable for everybody. But the problem is that the PTP is not there. That means like this entry is invalid. So we should ignore the entire entry. But for the second one, so PTP is set as 1. So you can regard that having this is like the value 1 in the entry. Then this entry is valid, but this entry only has the writable flag, but does not have a user flag. Then this memory region is only writable by kernel. Yeah. But it's also writable because it has a writable flag. For the last entry, so if we have a PTP and PTU up for those two flag bits, then this entry is valid, and then this entry is accessible by user. So both operating system and the user can access it. But the problem is that it does not have a PTW, so the memory region is a read-only. So this is how we can set and control the memory permission. Then you might be curious about why we need to set those kind of the memory permission flags in the page directory and page table. And this is because we will use a virtual memory system, and then the virtual address need to be translated at all time when CPU is trying to accessing the memory. So it's something like we will have a central point that all the memory request comes in, so that those requests will be coming from as like a virtual address. And then in translating the virtual address, we know that whether that access is a write access or read access, or current execution level is a user or operating system. And then in doing the translation, we can see the flag. And then if the flag is mismatching with the current access, then we can stop the memory access. So how we will utilize those permission check is as follows. So suppose we have a virtual address supplied like this. Then we will split the top 20 bits into like these two, and then we will apply the first memory access from CR3 to refer to the page directory, and then choose the page directory entry. And then suppose we are running a write access for this time. Then CPU will see the page directory entry and take a look at the flags. So PTP is there, U is there, W is there. That means like the entry is valid. And then this is a user accessible. And then it is also allowed for the write access. So for this page directory entry, we will allow any kind of access to the memory. But suppose our page directory search hit this block, for example, then this block does not have a PTEP. That means like that this entry is invalid. So what that means is that like there is no translation for that virtual address. So you can regard the entry without having PTEP as one as just an empty entry. And then after checking these kind of the page directory entry, and then we know that like all the permissions are allowed, so we just move on to the next phase. And then in the page table entry, we also check the page table entry and then check the permission flags. And then because the P, U, W are all there, so like we can allow, like even if this access is a user level write memory access, then we can allow that. So the important thing here is that there are two positions that we are checking the permission of the memory. So whenever we translate the virtual address, we first check the memory permission at the page directory, and then we will also check the page permissions at the page table. So there are two checks. And then you can regard that each page table entry will oversee the page permission for just one page, because this entry will be corresponding to the page 100,000, and then 3 more 0 as an address. So it will just manage that one page. But you can think it as like the entire page table will have 1024 entries. So the page table will oversee, entire page table will oversee the memory permissions for the 1024 pages. So suppose you have disabled one of the page directory entry. So that means you are actually disabling the entire page table. So you're disabling like the 1024 pages permissions by setting the permission at here. So in short, you can set the range of the permission to the range of the pages by setting the flags at the page directory. And then you can also set the individual page permissions at the page table. So the CPU checks the page directory entry first, and then check the page table entry. Yeah. So both page directory and page table need to allow the access to make the memory access possible in the CPU. And to concretize what we have just seen, And then let's do a little practice about like for the memory permissions. So suppose we have a virtual address of this one, but after following, so like to translate this, we need to cut it off at here, and then the 01020, that's the 5 digits. Then our like the lower 10 bits are like just the 20, but the upper 10 bits could be like the 0x4, yeah. And then that is not shown in here, but suppose after using those kind of the index to get the like a page directory entry, we've seen that the present bit and writable bit and user bit are all up. And then that's all up for the page table entry. Then the permission for this address is that this address is a valid address because both page directory and table entries are valid. And then this memory is accessible by the ring 3, the user application level, because PTU flag is all there for the directory and table. And then it's also writable because both entry allows writing to the memory page. Then let's take a look at a different example. So for the same address, suppose we set the permission flags like this. Then the resulting privilege would be because both entry has a valid present bit, so the address is valid, but it only has a writable bit in the page directory. So although page directory allows us to write on the memory, we cannot write on the memory because like the page table entry does not have that. So that's not writable. And then for the PTU, because both of them has the flag, then like this memory is accessible from the ring 3. So like the one question from the Zoom side, what would be the page directory address? So for the page directory, we will have a multiple page directory. For example, we need to have a one page directory for one process, because a process will share the virtual address space, and then each process will be having the isolated memory area. And to have that, we need to have a separated page directory for each process, and then that address will be stored in the CR3 register. So we don't know this page directory address at the start, but after creating one of the process, we will put the page directory address to the CR3 register. That's why we can always find the page directory address, and then we will just use the index from the address to traverse over the page directory and page table. And then for the next example, suppose we have a PTP and U up in the directory entry, but not in the page table entry, we have all the flags up. But in this case, I mentioned that like the CPU will do the memory permission check at the page directory entry first. So this permission setup does not allow writable memory because it does not have a PTW. So although the page table entry allows all the permissions, we need to get the intersection of the permissions. So this will be valid address, but accessible by the user, but not writable. And then another example. So in case the page directory entry allows all the permissions, but the page table entry only has a PTP. So in this case, so because both has present bit, so the translation is valid, but the page table entry does not have a PTU, so it will be only accessible by the operating system, not by the ring 3. And also it does not have a PTW, so the memory page will not be writable. And then the other example. So it also has conflicting permissions, like the allowing writable here, but the not writable here, but the table entry allows the user access, but directory entry does not allow user access. in this case, we also take the intersection of these two sets. So only we can regard that only PTP is available. Then this is a valid address, but not accessible by the user because page directory entry misses a user flag. And then it's not writable because page table entry misses a user flag. Question?
It is read only. Could the kernel write it?
So it is a read only, but even the kernel cannot write it.
Even
Yes, because even for the kernel, they do not have a PTW. So it's a read only. Yeah. And then the last one, I have two more. Yeah. So suppose we have a PTP and U here, and then missing PTP in the page table entry. So in that case, taking the intersection, that means like the PTP is not here. So the address translation is invalid. And then the same thing happens if we misses a PTP in the page directory entry, then even if we have a valid entry in page table entry, we should not honor that. So we will ignore this kind of translation as an invalid one. Any questions about like the setting the memory permissions? So the important thing here is that you need to take the intersection of the page directory entry, page table entry, then you will see that the exact memory permission arrangement. Then you might be curious about like this kind of the permission system has like some of the permission that we cannot set. So before getting into the some of the permissions that you cannot set, let's take a look at like what kind of permission we can set for kernel and user. So if you want to set a specific memory region to be read-only for kernel, but not readable by the user, not inaccessible by user, then how you can do that is like just set PTEP. Then the memory is inaccessible from user because there's no PTU, and then it's not writable, so kernel read only. So that we can have this this kind of the memory permission arrangement by setting PTEP only to the page table entry. And then suppose you want to make a certain memory region read only to both the operating system kernel and also for the user application. Then you can set it up as like having a present flag and also for the user flag. In that case, both, so it will not have a writable flag. So you both kernel and user cannot write, but because it has a PTU, so kernel can read and then user can read. So you can regard the PTP means like the kernel can read. And then PTW will add the writable permission on top of that. And then PTU will enable the user access. Then another flag setup we can do is like if we enable all three flags, then it's readable, writable to the kernel, and then readable, writable to user. So for these three setup, it's quite easy. Then can you set up the page table entry for having readable, writable to kernel, but the read only to user? So this is a conflicting case. So suppose we want to enable readable, writable, then we need to have present bit definitely. And then to allow writable memory, then we need to have a PTW. But to enable user access, then we need to enable, we need to have like PTU. But if we have all three, then it will become readable, writable to the user. But if we want to remove user access, then if we remove PTU, then user will not have access to the memory at all. So that means by in this kind of the memory permission setup, we cannot set this kind of the conflicting memory permission. And then same thing happens. Suppose you want to create a memory that is readable, writable to the user area, but read only to the kernel. If we enable all three flags, then that's kernel readable, writable. But if we remove writable, then that's also read-only to the user. A question?
So is this from the angle of like a user themselves trying to set permission?
Pardon?
Is this from the angle of a user trying to set permission?
No, it's operating system is setting the permission, but there could be a case that like the operating system would have a like restricted permission for that. Yeah. So that you might be curious about like why the operating system want to have like the lower permission than the user. Yeah, there could be a case. Yeah. And then I'm just showing that like that kind of the arrangement is impossible in the current page table structure. Yeah. And then the last one would be, so can we make the kernel inaccessible to memory, but the user can access the memory? So that's not possible because like to allow user to have read-write access, we need to enable all the flags, and that will naturally enable kernel read-write access. But we can actually set these kind of the memory permission setup. And to do that, we need to have a different virtual address. So with the current permission flags, there are cases about like conflicting permissions like this, because like we cannot have like we cannot enable kernel read-only while allowing user read-write. That is not possible. So the way of like the having a conflicting memory permissions, enabling that is we can have multiple virtual addresses to one virtual address, one physical address space. So the virtual to physical address mapping is N-to-1 relation. What that means is that like suppose you have a one physical address, then there could be multiple virtual addresses pointing to the same physical address. So the example is something like this. So one of the example is that suppose you are running like the many processes in your laptop, and then suppose your programs are all using the default shell called the bash program. So in that case, modern computers are very lazy. They do not load the multiple copies of the same program for serving the older processes. What they are doing indeed is, so they just having one copy of that program, and then map a different virtual address per each process. So you can think this example as, suppose you have a multiple Google Chrome tab, but all the Google Chrome tab need to load the Google Chrome's code to run. But in the physical memory, it only has one copy of that Google Chrome's code, and then it will share the mapping between multiple processes by having different virtual addresses, each of them. And then that kind of example also happens in JAWS, because after enabling virtual memory, so for example, so moving EAX to CR0, that means like the line right before this one is like the enabling the paging. And then this line actually enables paging. And then after enabling paging, it jumps to the F0 1000 to F. The reason is, so the next instruction wants to execute this address 1000 to F. But what JAWS does for their bootstrap virtual memory is that JAWS maps the virtual address 1 mega to the physical address 1 mega. So for the lower 4 megabyte region, so JAWS will directly map the virtual address to be the same as the physical address. And then this is for the special purpose for like making this kind of the execution smooth. So the reason is, after we put EAX on CR0, then our address translation model will be changing totally. So starting from here, all the addresses are virtual. So, but the problem is that our program was executing in 10002 this kind of address. So that address needs to be valid. So to make that address valid, we set the virtual address 1 mega to be the same as the physical address 1 mega. And then to have access to the entire physical memory, after enabling the virtual memory, well, JOS maps like the starting from the F000000, yeah. So prefixed with the F, yeah. So the top, like the 256 megabyte of memory, directly to the physical memory. So that's why like adding F on top of the address. So that will redirect the address to the physical address. If you remove the F, then that's the corresponding physical address. So that's how you can access a virtual address and the physical address. Yeah. So the important thing here is that like for one physical page, you could have virtually many virtual addresses for that. So let's get back to the conflicting page permission cases. So suppose you want to make one memory page as a read writable for the kernel and then readable for user. And to do that, you can set a virtual address 1000 as to map to the physical page 500000 somewhere, yeah, and then set the permission flag as a present and user. So it does not have writable flag. So for user, this is the read only. And then for kernel, for the same physical page, you can give a different virtual address. For example, F00500000. Yeah. And then we can set that permission as a PTP and PTW. Then kernel can read and write on this address, but that will result in the same effect because writing on this address and writing on that address will fall into the same address after the translation. But the important thing here is that the second address will allow writable access to kernel, but the first one will only have a readable access for the both side. And then for having a kernel read only and the user read writable, so that's also possible. For the user memory, we can map the virtual address as like this, and then set all the flags enabled. Then the user can make a read access, write access on this memory. But on the kernel memory side, you can get another virtual address and then just having PTEP, then it's a read only to kernel. And then same thing. So for the kernel, if you don't want to give the access, but for user, if you want to give the readable, writable access, then just having that address as like all the flags up, but remove the entry. So removing entry means that like not setting the PTP. Yeah. Then like you can remove the access from the kernel. But definitely, so for example, in this kind of the permission arrangement, if the kernel uses this address, so 0x2000, yeah, in that case, kernel can also read and write on the memory. Yeah. So that we cannot control that, but by having the address differently, so we can at least make the execution of the kernel do not violate certain the memory permission at runtime, so that we can do that kind of check on the CPU by setting the permission differently on a different address. So any questions about this point? Yes.
Kind of curious. So I imagine they only put invalid after like certain checks go off like certain invalid's, but wouldn't it be a waste to put memory to one of the tables if it's invalid? I'm trying to think of where we would ever use invalid.
So the invalid one is like the one without having the page table and PTP bit 1, right? And then so think about virtual memory. So suppose you just want to use 1 megabyte of memory, then you don't have to populate all the page tables, right? So we have a page directory and page table, and then suppose you are just using lower 1 megabyte. Then we only need to populate the first few entries of the page directory and tables, and then we can make the rest of entries as an invalid, and then we don't need to allocate page tables for that. So what I mean is that like although it is depicted something like this, so suppose we only need 1 page table, then we can set the page directories as a all invalid. Then we don't need to allocate these page tables.
The page table will have invalid.
So the page table starting with all the entries are invalid at first. Then whenever we allocate new memory, then we need to enable that by setting the P flag for that. Yeah. So for the permission settings, there are some of the caveats, and then when we access the virtual address, then the CPU will check for both the page directory entry and page table entry for the permissions. So it will check at the page directory first and also at the page table entry. So you need to make both entry to have a correct permission to allow the permission at the page level. So the general practice is that if you remove a flag for the page directory, then any page table under that one, page table entry under that directory entry will affect for the effect by that flag. So general practice is that having a more permission, so more open permission for page directory entry, but to have a more strict permission in the page table entry. So if there's no reason to restrict the permission for a memory region, then setting the page permissions at the table entry is the well-known practice. Because if you set a restricted permission of the page directory, then underlying the page table entry will all affect on it. And then if there could be the conflict between the kernel and user permissions. So with those three flags, we cannot make some of the permission arrangement. And in that case, we can have multiple virtual addresses to separate out those kind of the permission setup. And then let's delve into a little detail about the page directory and page table. So I told you that how we translate the virtual address is we will first refer to page directory with stored in the CR3 register. And then what page directory looks like is just the one page. So let's making everything simple. So we will manage the entire memory in a page granularity. And then to manage that, so we will use some of the structure, and then that structure is also in one page. And because one page of the memory is 4 kilobyte, and then each of the page directory entry. So we are using 32-bit computer for JAWS. So each entry will be 32-bit. That means each entry is 4 bytes. So 4 kilobyte. So we will have 1024 entries for the entire page directory for one page. And then that's why we will have a 10-bit index for the page directory. So you remember that whenever there's a virtual address, we take top 20 bits and then take top 10 bits to index this page directory entry. And then because our page size is 4 kilobyte, and then each entry size is 4 byte, we will have 1024 entries. And then to choose 1024 entries, we need 10 bits. So that's why we are accessing page directory entry with top 10 bits. And then the same structure goes to the page table. So page table is also one page. And then within that one page, we will have a page table entry as a 4 byte. Then it will also have 1024 entries. So that's why we are using middle 10 bits to index this array. So you can think the two-level page directory and table structure as you will have 1023 entries in page directory, and then that will be pointing to maximum 1024 page tables, and then within each page table there it will be 1024 entries per each table. then you might be curious about like what will be the size of the full-blown page table, page directory size. So in this case shows that the minimal size of the page directory and page table. Suppose you only translated address 0 to virtual address 0 to physical address 0. Then the virtual address 0 will, so if we index the page directory, then it will fall into the PDE 0. And then we need to have a page table for the PDE 0, then there is a page table. And then if we assume that we are translating address 0, then the page table index will be also 0. So if we have entry in here, then that's enough for translating address 0 to physical address 0. So the minimal size of the page directory and page table to translate the address is we need 2 pages. So 1 page for page directory and 1 page for page table. But if we have another translation, so some of the arbitrary address need to translate on the PDE3, then we need to create a page table for that. So that will require us to use like a 4 kilobyte more memory, just managing the translation. So let's take a look at how the size of the page table would look like. So we have a 1 page directory for the entire page table structure. So 1 page directory is 1 page, so that's 4 kilobyte. And then within 1 page directory, at maximum, we can enable 1024 page tables. And then the page table itself is also 4 kilobyte. So if we fully enable all the page tables under 1 page directory, then there will be 1 page directory and then 1024 page tables. So the entire size will be like 4 kilobyte added by 4 megabyte. So if we map all the addresses from virtual to physical for the entire 32-bit address space, 4 gigabyte space, we need a 4 megabyte like structure for doing that. So can you imagine that like that I went over like some of the page table size when we are talking about why pages are 4 kilobyte kind of thing. So if we are allowing byte addressable and then byte, so like if we can make the translation for like any kind of virtual address to physical address, then for 4 gigabyte of entries, 4 giga entries, we need to have 4 bytes for that. So if we have like a full mapping of the one address to the other address translation, then we should have a 16 gigabyte of page table. So that's very inefficient. But by having this kind of the 2-level tree structure, even if we translate any address in 32-bit space to the physical address, we can maintain that with the 4 megabyte of the additional space. Then you might be curious about like how it will be changed in 64-bit computers. So the things are changed in 64-bit computers is not about the page size. We will keep the same page size, 4 kilobyte. But the different thing in the 64-bit is that all the pointers need to be 8 bytes. Because 4 bytes, 32 bits are not sufficient to point like the entire memory space of the 64-bit computer. So then the number of entries are different. So within 1 page, so we previously can store 1024 entries because each of the entry is 4 bytes. So 4096 divided by 4 is 1024. But right now, so the basic page size in the 64-bit computer still remains in 4 kilobyte, but we have a 8 byte entry. Then we will only have like a 512 entries in there. So in 32-bit computer, we could have like the 1024 entries, and then 32-bit is the memory address bits, And then we will ignore lower 12 bits because that's the page size. And then we need to translate top 20 bits. And then this magically fits well with the 10 bits for the indexing page directory, 10 bits for the page table. So that's why we are translating top 20 bits and then using top 10 bits for indexing page directory and then middle 10 bits to indexing page table. And then in 64-bit computer, so that number need to be changed a little because we will have only we will only need 9 bits to index the page directory and page table because we will only have 512 entries in there. So in 64-bit computers, right now, we are not using 64-bit virtual address space. We only use 48-bit of the virtual address space. And then the reason is like the 48 bits is still huge. So that can support the 256 terabytes of the memory. So we are stick with that, but the later it could be extended to the 57 bits. And then let me tell you where the number 48 and then 57 comes from. So how the computers were designed was like we designed the 32-bit computer first, and then this kind of paging, and then all the operating system things were developed. And then later we developed the 64-bit computer. So when engineers designed the 64-bit computer, they tried to match some of the existing structures for when designing their virtual memory system. So what cannot be changed is like the page size. So suppose the page size is fixed, then that's 4 kilobyte. And then we will ignore the lower 12 bits in translating because our page size is that one. Then suppose we have a 48 bits of the address space. Then 48 minus 12 is 36. And then in 64-bit, we can only use 9 bits to index each of the entries, tables, that kind of structure. So if we divide 36 by 9, then that's 4. And that means we could have 4-level page table to translate 48-bit virtual address to the physical one. And then let me show you how it is linked with some of the graphics. So when we translate the 32-bit address to another 32-bit virtual to physical, then we ignore the lower 12 bits, and then we use top 10 bits to index page directory, and then middle 10 bits to index page table. That's because each page directory and table will have 1024 entries, which will be indexable by 10 bits. But in 64 bits, we will ignore lower 12 bits. But recall that each of the page table directory or some other tables, so we have a more nested structure than 32-bit. So it's a 4-level right now. Yeah. And then in each of the table, we only have 512 entries. That's because 4 kilobyte divided by 8, because 64-bit is 8 byte. So because we only have 9 bits to index the page table. So 11 plus 9. So actually we ignore 12 bits, and then 9 bits more, 21, 9 bits more, 30, 9 bits more, 39, and then 9 bits more, 48. So with the 4-level page table, so each of the table can consume 9 bits. And then at the end, we can add the offset 12 bits. So 4-level page table, 4 multiplied by 9, 36 plus 12. So you can support up to 48 bits address space. So like it was a technical decision to only allows like the 48 bits of the address space. And then that decision was made in like the 2001 or 2-ish, because like the current architecture of the 64-bit Intel. So the one interesting thing here is that the 64-bit Intel architecture do you know what is the official name of that architecture? So the official name is AMD 64. And then you guys might be curious about like I'm telling about the Intel processor, but where's the AMD? That keyword comes out. So the reason was, so in 2001 or 2-ish, so Intel was planning to have a new CPU called Itanium. So it's totally different with the x86 architecture. So they tried to withdraw the backward compatibility and then would like to design a new computer. And then that is so-called IA64, Intel architecture 64-bit. Yeah. And then while Intel was pushing that end, their competitor, AMD, so they start with creating the CPU, the copy of the Intel x86 for the 32-bit. But in 2003, they developed the AMD Athlon 64, which supports the first 64-bit architecture. But they just extended 32-bit Intel machine to be a 64-bit. So what they did is like there's an EAX register, but they made it as a RAX register, which is a 64-bit. So what AMD did was a very simple extension, but in the market, that kind of the 64-bit transition, because it supports the backward compatibility, so that won the market. That CPU won the market. So another interesting story is like although Intel put a lot of money to develop the Intel Itanium, so we cannot see any kind of the commercially selling that product because that product was completely dead. Yeah. And then that's why we call the 64-bit architecture for Intel machine as AMD 64, because AMD applied for the patent first. Yeah. And then in this AMD 64 architecture, so at that time of the decision, like in 2001, 2, 3, yeah, in that era, so having a 256 terabyte of memory was like the plenty. So right now it's quite feasible, but at that time, so even for like the having a 100 gigabyte of memory takes like more than $1,000. Yeah, now right now it's much cheaper than that, but it was not like that. So 256 terabyte was huge in that era, but in the future it could be small. Then what we can do is right now we are using full level page tables, so it can translate 48 bits of the virtual address space to the physical, but we can extend one level up, and doing that will add 9 more bits, because what we will do is like we will add one of this layer up here, and then that can only consume 9 bits for the translation if we do not set the size of this table as like the bigger than a page. Yeah. So if we follow the same engineering decision, then we will have like 57 bits of the address space. And then this is actually implemented starting from Intel's 9th generation CPUs. But right now, most of the operating system don't use it, because if you don't use this much of memory, then having an additional level will incur additional memory access, so that could be the performance overhead to the system. So the implication here is that, so the virtual address translation will involve memory access when we work down this kind of table. So in 32-bit, it was just a 2-level table, so 2 more memory access. But in 64-bit, it requires 4 more memory access to get the virtual to physical address translation. So the address translation itself is a very heavy operation, and that's why we have a TLD to cache that. And then this kind of the address translation problem gets more complex when we introduce the virtual machines. So I believe like some of you guys have run the virtual machines on your laptop or computers. So it's something like when you are running Mac, you can run the Windows on top of it. So using Parallels or VMware, that kind of software would fall into using up this kind of the structure. So in that case, So you can regard like you just disregard this top level diagram here for now. So you can regard this as a physical memory, and then this as a application memory in the operating system. But when you introduce the virtual machine, then your virtual machine will think that they are running in the physical machine. So this virtual memory will serving as a virtual memory for physical memory for this virtual machine. So there will be translation between, so you can regard this as a Windows to the Mac user level memory. There could be one translation. And then Mac user level memory to the physical memory. There will be another translation. So what that means is that, so the actual page table translation in the virtual machine is something like this. So you might be haunted by like this kind of the diagram, but you can understand it as, so the CR3 register will store the page directory address, the first page directory address of the guest operating system. So CR3 will store somewhere in this space. So that's not the actual physical address. This is a virtual address of the Mac. So that's why that address need to be translated to get the physical address of the next one. So you can see that in this direction, the translation goes from the Windows, the virtual machine. And then whenever you have a physical address in the virtual machine, then that need to be that's the virtual address of the operating system. So that need to be translated in the operating system. So this is so-called a nested page table. And then if we are with the 4-level page table access, then we need to have like the 20 memory accesses to translate one virtual address to a physical address. But the CPU internally magically do this automatically whenever we need to translate the virtual address to physical address. And then like that they are all honoring the page directory and table structure that we just learned. So it's the operating system designer's job to set the page table directory well, and then supply that to the operating system and the applications. And then like this is the basics of the virtual memory system. And then by having the page directory and page table, and then CR3 register, we can have a CPU to accept virtual address and then find where the actual memory is in the physical address. And then by giving that kind of capability, we can freely use the virtual address space because there's no binding between the virtual to physical addresses. So we can pick any kind of virtual address to show some of the view of the physical address. So good. So please recall the goal of the virtual memory. So there was a goal for transparency. So whenever we use the virtual memory space, so I just put the code heap library stack in anywhere. So like what that means is that like the programs do not need to care about like what other programs are running on the system. They just use their address space freely. Yeah. And then the isolation here means that like this kind of view can only be available to the specific process. So what that means is that like the other process will never have the same view because we will have a different page directory and table per each process. But one of the good thing is that like we can also share the common part across the multiple processes. So for the performance reason, how we map the kernel and then user memory is that. So as an example in Linux, we map the top 1 GB of the region for the kernel and then map that to all processes. So this is okay because like we have a PTEU flag in the virtual memory system, and then we remove PTEU flag to all this region. So like the user applications can never access these memory regions. But one of the good thing about doing this is that like whenever the user program requests access to the hardware, for example, calling the function printf to printing some of the characters on the console kind of thing, yeah, they do need some of the code in operating system, and then need to be run on the memory space. And then having a shared kernel mapping allows like that we don't have to load the kernel every time we need whenever we need that. But the good thing is like we can set the memory permission, so this area can only be accessible by the operating system. And then like this is an example output that I got from the 32-bit Linux machine. And then if you run cat proc self maps, so this is not actually the file. So this is the file-like interface. Then if you read on it, then it will give the information about the currently running process for their memory mappings on Linux. So you can see that when I run bin cat, because I'm running this cat binary. So self means like self refers to the this binary program. And then you can see that this program is loaded in these addresses. And then some of the libraries that supports this binary program, it will be loaded in some different addresses. And then stack is at here. And then you can also see that readable, writable, and then executable, that kind of the flags. And also P here means that the PT present. Yeah. Otherwise, so this only shows like the valid memory mapping. So that's why all the memory regions are with P. Yeah. So if there's an OP flag, then it is not even shown in here because that's an invalid mapping. And then this is the example of like when I run the different program. So I included this because heap starts at like the 8db6, but in here heap starts at 8910. So that means that two program can use like a different heap address. There's a transparency. So like the one program do not need to take care of like the heap address need to be fixed or something like that. So they can set any kind of the addresses because like the virtual addresses are plenty, and then there's no restrictions on using that for a process. And then for the stack address, so for this program cat, it uses stack from bf9a, but on the another run on the bin more, it uses stack for the bfa7, so that they can freely choose using any kind of address like that. And then the reason why I show like this kind of thing is that like we will do the similar thing in JOS Lab 2. So JOS Lab 2, you are required to preparing the kernel part of the page table and then share that to all of the environment, which we will use that as a process memory. So in Lab 2, you need to manipulate the page directory and page table, and then to enable this kind of the memory mapping in the page table. So each of the entry, I'm not sure you can read on the screen or not. So you will see that readable, writable for kernel, not readable, writable for user. That means you need to set the flag as a PTE, P and PTW, but PT, not PTEU, because you need to block the access to the user. And then the read only to the both of sides, then like you need to set PTP and PTU for that. So based on like this kind of the diagram, after you create the virtual memory system, you need to create this kind of layout for that. So the summary of the things that we learned for today. So we learned about like how we can control the memory permissions using the permission bits in the page directory and page table entry. So because CPU will check the page directory first, and then we'll also check the page table entry. So to get the correct permission, we need to get the intersection of the permission flags in the page directory and page table, and then we can identify what kind of the permissions are applied to there. And then the virtual memory is not one-to-one mapping. So for one physical memory page, we could have virtually like the n number of many virtual addresses. So if there's a conflicting permission arrangement, then like we can assign them by having a different virtual address for kernel and for user. And then for the virtual memory layout, so after building the virtual memory system, we can freely use the virtual memory, but for some purpose, like we want to share the kernel part of the memory, yeah. And then to do that, we can securely do that by removing PTU flag from those regions, and then you will practice that in JAWS Lab 2. Any questions for the things that we learned for today? Yes.
So in previous lectures, we talked about how two different physical addresses can use the same virtual address. So how, if two different physical addresses are using the same virtual address, can we map backwards from the virtual?
So we cannot map the two physical addresses have a one virtual address, but we can do the opposite. So if I depict that, so suppose this is a physical address. Then we have a one page here. And then you can have a virtual address, maybe virtual page 1, and then virtual page 2. And then we can map this to here, and then we can map that to there. So that we can have this kind of the virtual to physical mapping, but not the opposite. So n to 1 mapping. Yes. Yes. So like the main purpose of that is like this. So suppose we want to have a readable, writable permission for user, and then read-only permission for kernel. And then if the kernel knows this address, then they can freely access readable, writable. So it's not about like restricting the kernel from making that access, but it's more likely some practical use of this kind of thing is that suppose as a user level application, you need to read and write on some of the data, but you want to implement some of the process monitor. So what that means is that like you want to at the operating system level, you want to monitor if the application is doing malicious or malicious activity or not. Then we just want to take a look at the memory of the user application. But suppose we are running some of the code in this memory region. Then suppose the coder of the that kind of antivirus system made a mistake. Then they mistakenly tried to overwrite some data of the application. And if we use this address, it will fail. Then we can debug that. But if we use this address, then we cannot even know that bug is existing. Yeah. So this is somewhat debugging purpose. Yeah. So practically, it does not make any sense because if kernel knows this address, they can always readable, writable, and then even kernel can change this permission flag too. Yeah. So it's not about like the kernel do not do something. It's more likely like that some of the techniques to catch the error if there's some of the violation happens. Yeah. Any other questions? Then let's finish the lecture for today here. And then please watch the tutorial videos for the lab 2 and then work on those.